All right, so another example of limits at infinity. X is getting larger and larger and larger. So this is a rational function, and it turns out there's a trick here that I want to teach you. There's an even more specific trick that some of you know from college algebra, but let's learn the general trick which will work in all situations. So I want you to look at the degree of the bottom. Okay, the degree of the bottom is just the highest power of x downstairs, and that is 3. And then you need to multiply top and bottom by 1 over that power of x. So 1 over x cubed, top and bottom. I can multiply, because I'm only multiplying by 1 the way that I've written it, but I'm going to multiply this across there, and then this across here, and we'll see some familiar limits pop out. So when I do this, I get the limit as x goes to infinity of 1 minus 4 over x cubed over 1 plus 3 over x squared. Multiplying this by this, the x's cancel, leaving me an x squared, and then I get plus a 4 over x cubed. Now at this point, x is going to infinity. It's getting arbitrarily large. So x cubed is certainly getting arbitrarily large, and it's always positive, by the way, because this is positive. So this limit, you can see, has the form 4 over infinity. You know the bottom is positive and the top is positive, and so this thing is going to 0. And the same argument here going to 0, and the same argument there, all going to 0. So we actually write that like this. You can actually put a 0, 0, and 0. All those are getting small now, and you're left with 1 over 1. You can say, okay, look, this is 1 over 1, which is 1. So the limit is 1. Now, the real trick is when the degrees are the same, you have a cubic upstairs and a cubic downstairs, you know the answer is going to be the ratio of the leading coefficients. It's always going to be 1 over 1. Now, some of you were like, well, then why do we have to do all of this? Well, because it's an example of this particular larger trick that you need, and I will expect you to be able to do this algebra. So please don't just write down 1 over 1. The answer is 1. Some of you asked me, how much work do you need to show? In this situation, I would want you to be able to do the algebra here, because we'll need it later on. All right, well, let's go ahead, and I think I'll slide this up actually on the slides here on the screen. So I want to mention a definition. So we're going to call a horizontal line y equals L a horizontal asymptote for a function f of x if either, the limit as x goes to infinity of f of x is L, or the limit as x goes to minus infinity of f of x is L. And so I have a picture that I've sort of sketched here, and I'll slide this up as well. And you can see as x gets larger and larger and larger, the function is getting closer and closer and closer and closer and closer to this bottom asymptote. So we'll call this guy, this is actually y equals -1, and this one is y equals 2. So here you can write down the limit as x goes to infinity of f of x is -1, and then upstairs as x goes to minus infinity, as x goes to minus infinity, let me clear that, the function is getting closer and closer and closer and closer to 2. And so we get these two limits here. The limit as x goes to minus infinity of f of x is now 2. And so what I want you to realize is that these limits actually tell you that y equals 2 and y equals -1 are both horizontal asymptotes for our function f of x. And I'm using HA to abbreviate horizontal asymptotes. I should have written that up here. So we'll just squeeze that in. There we go. All right, so let's end this video here. And then I've got a whole series of examples I'm going to do. I don't know if it'll be 1 or 2 videos, but let's do those in the next one.